Okay, now we'll see 11th experiment of whose title is Natural Frequency of a Spring Mass System. Here, the aim of this experiment is we want to find what is the natural frequency of the given spring mass system. If you look at the problem description here, two springs which are connected in series, and for the two springs a mass is attached on the bottom. So he has given the stiffness of those two springs, which is equal to 1000 Newton per meter, and also mass is given as 5 kgs. So now for this we want to find out what is the natural frequency. So far we have solved different types of analysis using the software. So in structural analysis, we have seen static structural, and also after that we have seen eigenbuckling analysis also. Similarly, in case of thermal, we have seen transient steady state analysis also. Again, this problem comes under structural analysis. In this, we'll take up the another analysis which is used to calculate especially for the frequencies, natural frequencies of the system. That we'll call it as a model analysis. So we'll try to solve this problem using model analysis in the software. So now to solve this problem, before going to that, we'll see we know analytical solution for this, and given the formula for the analytical solution also here. The natural frequency Fn is given by 1/25 into square root of K equivalent divided by M. So where K equivalent is nothing but the equivalent stiffness of both those two springs which are connected in series. So when two springs are connected in series, the equivalent stiffness formula is something like this: K1 K2 divided by K1 plus K2. If you substitute for K1 and K2 as 1000, you will get your Ke as 1000. 500 Ke as 500 Newton per meter. If you substitute K1 1000 and K2 1000, it is 1000 into 1000 divided by 2000. You get your Ke as 500 Newton per meter. You take that and substitute here. 500 divided by M is 5. So 500 by 5 will get 100. Square root of 100 it is 10. 1 by 10 by 25 is nothing but you'll get 1.59 hertz. Here the units for this frequency here it is hertz. If you don't use this 1/25, you'll get in radians per second, but the software will give you the frequency values in terms of hertz only. So we have to use this formula. So if you substitute the data and compute it, you will get it as 1.5915 something. So on after that, we don't bother about what is the values. 1.59 will take up to 2 decimal points, which comes out as 1.59 hertz. So now we need to take this analytical solution and we need to compare that with the simulation solution. So now to solve this problem in the simulation, so it is a simple problem. We can solve it within 5 to 6 minutes. We can solve this particular problem. So to do that, first we have to create the FE model. So if you look at this diagram, it will tell you what is the FE model. So you can clearly see that here there are three elements: 1, 2, 3, three elements, and three nodes also. One here, one node. Then the connection of the two springs. The two springs are connected at this location. Here you have one more node, that is node number 2, and end of the bottom spring, that is the third node. So that means we need to create three nodes as well as three elements. In that three elements again, so the first element here, first element is for the first spring, second element is for the second spring, and third element is for this mass. So to create these elements for the springs, we'll use a new element. So far whatever elements we use, those are not suitable to model the springs. So for create the element 1 and 2, we'll use combination 14. So which is suitable to model springs having stiffness as well as damping. Anyway, in our problem we have only stiffness, we'll take the damping as 0. Then to model the third element, that is the rigid mass, here this mass is a rigid one, we need to use another type of element which is mass 21. So that's what I written here in this. So your FE model consists of three elements and three nodes. Two node combination 14 elements are used to model the springs. So for modeling the springs, we need to use combination 14, and for modeling this mass, we'll use mass 21. And Respectively, we need to input their values. So springs have a stiffness of 1000 Newton per meter and mass as a 5 kg. So while defining these elements, we need to input these element attributes. That is, for mass 21, you need to define mass, which is 5 kgs. For spring, you need to define stiffness, 1000 Newton per meter. If it has damping also, you can define damping also. But here, we'll take the damping is 0. So we are calculating undamped Nusselt frequency only. So, but then, okay, so like we can select the what I mentioned, we can select the elements and we can define the nodes. But to define the nodes here, what we need is we need the coordinates. For node 1, what are the coordinates? For node 2, what are the coordinates? For node 3, what are the coordinates? So for that, he has not given what is the length of the spring, top spring as well as the bottom spring. So then what we'll do is actually the length is doesn't matter here, as long as if you know the stiffness value, whatever may be the length of the spring, it doesn't matter here. So you can take your own length dimension. That means first we'll take the node 1 as 0, 0. Then the length is, see here the spring is in y direction, so you need to change only the y coordinate. So you can take any value for y coordinate. So for the second node, so that is, let us say y coordinate for second node, I'll take it as minus 0.5 because it is coming down here. I'll take negative value. So that is in the negative direction. See, you can see your positive y is upward. So I'm coming down. So I have to take a negative value. So therefore it is, I can take minus 0.5 or minus 0.1 or 1, whatever it way. So you have to take the negative value. Whatever may be the value, you can take it. It doesn't matter. Similarly, for node 3 also you can take as per your coordinate wish. You can select the y coordinate. So let us take that. Here it is minus 0.1 for second node and minus 0.2 for third node. So we'll create the three nodes. So once you create the 3 nodes, you join node 1 to node 2 using combination 14 elements. So you'll get the first spring. Then using node 2 to node 3, if you connect node 2 to node 3 using again combination 14 elements, you'll get the second spring element. Then mass 21 is a single node element, whereas this combination 14 is a 2 node element. That means to define the element, you require 2 nodes for combination 14, whereas for mass 21, you require only 1 node to define the mass. So therefore, I'll select since the location of the mass is at this point, I'll select only node 3 to define the third element for this mass. So I'll use the mass 21 element type to define this. So that's it. So once you've done that, so you can solve it. So before going to solve also, we can specify some more behaviors of the springs. So here our intention is we want to find out what is the Nusselt frequency of the system, and the spring moves in the vertically upward direction. When the mass is disturbed initially, that means if it is full down, then if you leave it, so it will oscillate with certain frequency. That frequency we'll call it as a Nusselt frequency. So whereas that means our mass is oscillating only in the vertical plane in the upward, up and down direction, then are in the y direction. So but here in our software, whatever nodes we created here, those nodes will have 2 degrees of freedom or maybe 3 degrees of freedom. So therefore, whatever degrees of freedom unnecessary there, we need to eliminate them. So to eliminate them, what we'll do is, while defining the behavior of the spring, we can do that. So that means whether I'm defining the spring using 2 nodes here, so I can define its behavior also. That means whether it is a linear spring or a torsional spring, or whether it is a 1-dimensional spring or 2-dimensional spring, or maybe 3-dimensional spring, like that I can define it. Similarly for mass also, whether you have only linear mass or you have a linear mass and linear movement and movement of inertia also, like that. So depending upon the type of the problem, here it is a linear problem only, so I need to define only, I need to treat this one as a 1-dimensional spring, and I need to define only mass. So I don't require any mass movement of inertia. So because here it is a linear system. So by keeping all these points in mind, now I'll take you to the software and we'll see how we can solve this problem in the software. So I already opened the software. So I given the name as a title for this job as the Nusselt frequency. So then we'll proceed with this. So I think I know how to do up to this point. So go for preferences. If you want, you can select structural here, because this comes under structural analysis only. So now first we'll add the element types. So in that we need to add two element types. So one is for the springs, that is combination 14. So you scroll down it here. So you come down here, you have a combination. Then in that you have a spring damper 14 is there. You select this one, spring damper 14. Then under these options, like I mentioned here, we need to specify the behavior of the spring here itself. So you click on the options here. See, DOF selection for 1D behavior, because our springs are behaving only 1D, so they are permitted to translate in only y direction. I need to select it as a longitudinal UY degrees of freedom. You can see that other one also, torsional rotation X, torsional rotation Y, torsional rotation Z. That means the spring, you can use spring element, same element, you can use it for the linear translation degrees of freedom or rotational degree of freedom also. So now here we need to, what we need to select is, we need to select longitudinal y uy degree of freedom. Click OK. Then add the next element type to define the mass. So here you need to click on the structural mass. You have mass 21 element is there. Then select this and click OK. Again, for this mass also you need to specify its behavior. So for that, here in the key point option, a rotary inertia is not there for my mass. So what I have to do, select here is 2D without rotary inertia, because it is only linear mass. You don't have mass moment of inertia. So we need to select this option. Okay, once you done this, you close these element type options. Then you go for the real constants to define. For springs, we need to define the stiffness, and for masses, we need to define the mass moment of inertia. So right now, nothing is defined. Now I'll click on add. So first, I'll define the stiffness of the springs. For that, I need to select here type 1, that is the combination 14. Then click OK. So now it is asking me, see here, real constant set 1, we are defining for the spring. It is asking for spring constant, damping coefficient. If it is not, damping coefficient is non-linear, what is that coefficient also? Similarly, initial length and initial force, like this it is asking. So we'll treat all these values as zeros. That means we don't bother about the remaining values. We'll input only the stiffness, because that is the only given data in the problem. So we'll enter K is equal to 1000 and then we'll click OK. So we define the stiffness of the springs. Both the springs having same stiffness here, 1000 Newton per mm. Suppose if K1 is 1000 and K2 is some other value, 2000. So we need to define two sets for the two springs. Since here two springs are having the same stiffness, only one real constant set is sufficient, because we'll use the same for the both the springs. Then one more set we need to define for the mass. So here you need to select now mass 21. Then click OK. So now see, you can see it is asking for the mass. So in the problem it has given mass as 5 kgs. So enter 5, then click OK. So now remember, you can check those things also, and also you need to remember which set you define for what values. So here you go for properties. Here you can see that real constant set 1. So in this you can see that first value is 1000 and remaining values are zeros. So then you come to the rail constant 2, first value is 5, remaining things are 0. That means, so this is 5 kgs, for this is set 2 is for mass and set 1 for the springs. So like that also you can check your what I can say properties. So now once you define the real constants, here no need to define the material properties, because we already defined through the real constants those values. So directly we'll go to the modeling and we'll create the nodes first. So go for modeling, create nodes. So in active coordinate system, so first one is 0, 0, 0. Simply I'll click on apply. Then second one is, I need to take it as minus 0.5 for the second node. So apply. Then I'll take the third one as minus 1. So here, like I already told, these are the choices. You can take any distance, it doesn't matter. So once you've done that, then you need to create the elements. So I'll go for elements. Then here important point what you need to remember is, before defining the elements, you need to set its attributes. That means if you are defining the spring elements, you need to set the spring properties through real constant set. If it is a mass element, you need to set the properties of mass through again the real constant set. So first we'll define the spring elements. So for that we need to set the spring properties. So here that means you need to set the real constant set. So here we have two sets are there. We define two sets for the two sets of real constants. One is for the spring, the second one is two is for mass. So here first I need to select it as one. Of course defaultly it is selected as one only. So we'll take that like that only. So we'll click OK. Then we'll use auto number option through nodes. First I'll select node 1 and node 2 to define the first spring. Click apply. Then select node 2 and node 3 to define the second spring. Okay, two springs are created here. Then we need to define the mass element. So for that here, now we need to change the element type because combination 14 is used for the springs. So for mass, you need to select mass 21. And similarly, you define the real constant 2 for the mass, that is M5 kgs. You need to select the real constant set also 2. Then again, go for auto number through nodes, click on that, then select only node 3. Only you have to select only node 1. Only one node is selected, that is node 3 only you need to select it. So don't select any two nodes. So if you select two nodes, it will create the mass elements at the two nodes. Okay, right. So I'll click OK. So then it is also defined. So if you have a doubt whether you created them properly or not, again what you have to do is you go for list elements and nodes and properties. You can check it here. So whether you define material doesn't matter because we don't bother about the material properties here. You have to check only whether your element type and real constant set, whether do you define them properly and also their corresponding nodes. You need to verify that. If you feel that it is okay, then you can move on to the next step. So that is solution. So before solution, you can apply the loads here also, or in the solution also you can apply the loads. So okay, you will apply the loads and boundary conditions. So for that, we'll apply structural displacement on nodes. So in the diagram clearly given this top end is fixed. So I'll select this top node. I'll click OK. I will apply all degrees of freedom for that. So now it is fixed now. So for node 2 and node 3, we don't want to allow this displacement in the x direction. That means this node is not permitted to move in this direction. So you can see x direction is horizontal and y direction is vertical here. Okay, now we need to constrain node 2 and node 3 also in x direction, so that displacement in x direction is for these two nodes also constrained. So I'll select node 2 and node 3. I'll select ux is 0. Okay, so then we need to solve this problem to find out the natural frequencies. So for that, we need to set the analysis type as a modal analysis. So go to solution, click on analysis type, click on new analysis. Now we need to select it as modal analysis. So to find out the in any problem, if you want to find the natural frequencies, you need to go for modal analysis only. So after selecting model, you click OK. Then in the analysis option, how many number of natural frequencies you want, you need to enter. So depending upon the number of degrees of freedom in your system will have those many number of natural frequencies. So if I say here 4, it will try to compute 4 natural frequencies. So for the given system, but in our problem, we have only one natural frequency because our system is a single degree freedom system. There is only 1 degree of freedom in the system. So you'll get only one natural frequencies. Even though if you give 4 here, so it will give you only one natural frequency. So here, whatever default is there, you click it OK. Don't change anything. You click it OK here. So now we need to go for solve. So solve current ls, click OK. So don't bother about these warnings. So you can ignore it, or if you want to know what is that warning, so just go to the output window here, and you can see that here you can see the warning. There is a node 1 and node I and node j of element 1 are not coincident. So node 1 and node j of element 2 are not coincident. So these are the warnings, 2 warnings you got it. So decided is the data produced 2 warnings. Those 2 warnings are node I and node j of element 1 and 2 are not coincident. That means, so we consider some length for the spring. We consider, so node 1 starts here, node 2 starts here, we consider some length. So, but we are not defined any length. So that means that's why it is saying that node 1 and node 2 are not coincident. It doesn't matter whether they are not coincidental. So as long as your free force is free tension force in the spring is 0, it doesn't matter. So you can simply ignore this warning. So then once you click yes, then it will solve for you. So once solution is done, to see the natural frequency again, what you need to do is you need to go for output window. In the output window, you can clearly see that it will calculate you the natural frequencies. If you scroll up down, here you can see mode 1 natural frequency is 1.5915 or something. So beyond that, we don't bother. So up to these many number of, after decimal point, we don't require these many. We'll consider up to 2 or 3, that is sufficient for us. See, while inputting the number of modes to be expanded or extracted, I given it as a 4, but it is giving only one natural frequency. So because your system has only one free degree of freedom, it will give you only one natural frequency. That means your system will have only one natural frequency. Even though you are requesting for 4 or 6 or any number of frequencies, it won't give you all those frequencies. It will list only one natural frequency because actually your system has only one frequency. Okay, so I think this is our value. So 1.59. So this matches with our analytical solution. So then that's it. So we need to do only up to this. So we need to compare this value to that, and we try to find out what is the percentage of error. If the error is less than 1% or 2%, your solution is accepted. Okay, so this is how you can solve the problem. And if you want to see the here how it is going to deform, that is the mode shape. So for that, what you have to do is you need to go for general post processor, and also here if you click on result summary, also it will show you the frequency. So 1.5915 time or frequency, but here it won't tell you what are the units for this frequency. If you look at it in the output window, then only you will know the units. So in the output window only you mention the units as heads. You can clearly see it here. See frequency in heads. So here he written only the units, but here simply it is saying time or frequency 1.5915. So it don't tell you what are the units here. So if you want to see the units, you can go for the output window. So or else if you know, definitely the software will give you the units as heads. So directly you can take the results from here. So then if you want to animate it, how it is going to vibrate, or if you want to see, you can see that I already told to you, this is a spring and this is a spring and this is a mass. So if you want to visualize those things also, what you have to do is you need to go for style here and you need to check this rail constant display on, element shape is on, then it may be displayed as springs, multiplots, go for multiplots. See now it is placing something, a symbol something similar to the springs having stiffness K or K0. Here you can see that mass element is there, so it is displaying mass element as M0. So now if you want, you can animate it also. So go for animate and then mode shape. So we have only one mode shape, so that will be animated. So how? Okay, plot controls, animate or deform shape. Okay, before that what you need to do is you need to read the results. That is important thing. Read the results. Of course, first set only we have, then you can animate it. See, it is moving down, up and down. Okay, if I fit window, if I want, I can increase the speed of the animation just by making the delay equal to 0. See, now we can see it is animating something like this. So it is moving up and down. So that means only we allowed the translation. Okay, so this is only for visualization purpose only. No need to keep this one in your record also. So just you note it down the what is the natural frequency and you know that is sufficient for this experiment. Okay, so with this we'll close this one. Maybe we'll meet in the next class with the another experiment. That is the last experiment, which is 12th one.